are going to see about the laws of photoelectric effect. The above detailed experimental investigations of photoelectric effect reveal the following facts. Number one is, for a given metallic surface, the emission of photoelectrons are just coming out, and it takes place only if the frequency of the incident light is greater than the particular frequency, minimum frequency. That frequency is known as threshold frequency. So, below this minimum frequency, there is no more electron emission. So, after reaching the threshold frequency, the photoelectric electrons can be just emitted from the surface. That means, so this is a metal piece. Here the free electrons are just moving here and there. So, up to reach the threshold frequency, there is no more level of electrons just be having nature of just emitted from the surface. So, when the threshold frequency, that minimum frequency be just be reached, then automatically the electron emission can be taken place. So, below the threshold frequency, there is no more electrons be just be emitted. Then in the second case, for a given frequency of incident light, that is above the threshold value, the number of photoelectrons emitted is directly proportional to the incident of the incident light. That means the saturation current is also just directly proportional to the incident intensity of the light. That means here a particular frequency of light is just incident on the metal plate. Then the number of photoelectrons emitted are just directly proportional to the intensity of the incident light. That means more intensity, more light will just be falling on the surface of the metal plate. Then more number of electrons be emitted. So there is a linear curve. When the more intensity of the light is just falling on the surface, more electrons be emitted. Lesser intensity is just falling on the metal surface, lesser number of electrons be just emitted. So they are directly proportional. Even for reaching the saturation current value also just directly proportional, because for more intensity, more electrons be reached. So the saturation current is also having a directly proportional to the intensity of the incident light. Then the maximum kinetic energy of the photoelectrons is independent of the intensity of the incident light. That means here when the some quantity of the intensity of the light is just falling on the surface of the metal, then automatically the kinetic energy of the free electrons will just be increased. To reach a maximum kinetic energy, that maximum kinetic energy is independent upon the intensity of the light. Even minimum intensity will just be falling on the light, the kinetic energy K max B is no way just related with the intensity of the light. That means lesser intensity also K max is one value, mean for more intensity also the same K max be just be obtained. So that's why maximum kinetic energy of the photoelectrons is independent upon the intensity of the incident light. The next point is the maximum kinetic energy of the photoelectrons from a given metal is directly proportional to the frequency of the incident light. That is, the maximum kinetic energy of the photoelectron for a given metal, because the Kmax differs for different metals. Depending upon the metal characteristics, the maximum kinetic energy of the photoelectrons be just differed, but it is directly proportional to the frequency of the incident light. So frequency mean, here more frequency mean more electrons, more kinetic energy be just be observed. Lesser frequency be just be incident on the surface of the metal mean lesser amount of energy will just be obtained by the electron. So the maximum kinetic energy value of the photoelectrons just be for a particular metal is directly proportional to the frequency of the incident light. More frequency, more maximum kinetic energy value be more. Lesser frequency means then the maximum kinetic energy also lesser. The next point to remember in your mind, there is no time lag between incidence of the light and ejection of the photoelectrons. See, here on the base of the wave theory, it takes more time to release the photoelectrons. But what is the actual fact observed in the experimental result? Here, incidentally, when some intensity of light is just falling on the surface of the photoelectric material, within a particular time interval, without any lag, it emits the photoelectron. So there is no time lag between the incidence of light and the ejection of the photoelectron. They are a simultaneous process. Once the photoelectric phenomena has been thoroughly examined through various experiments, then the attempts were made to explain it on the basis of the wave theory of light. See, the photoelectric emission phenomena be just explained only by the particle theory, not by the wave theory, because the obtained result and the wave theory concepts are entirely different. So, next we are going to see about the concept of quantization of energy. What are the concepts which are just behind the quantization of the energy? So, when the classical wave theory, there are so many failures be obtained. So, the failures of the classical wave theory be explained first of all. From the Maxwell's theory, already in the unit 5 itself we have just in detailed study of the Maxwell's theory we have gone through the concept. So, the light is an electromagnetic wave which consisting of coupled electric and magnetic oscillations. Electric oscillations also there. So, whenever we have your electric field, then automatically magnetic field also just be produced in that particular place. So, the electric, it is a coupled effect of the electric and the magnetic field that move with the speed of light and exhibit typical wave behavior. So, here the speed of light, it is very high. So, the same speed of light, magnetic oscillations here and producing here and there and just traveling in the speed of light and just producing the light wave. So, first we are going to explain the experimental observations of the photoelectric effect using the wave picture of light. That is the failures. The experimental result and the wave theory concept are not just coinciding with each other. The first point to remember in your brain is, when light is incident on a metallic surface, there is a continuous supply of energy to the electrons in the metal surface. Here, here this is a metal surface, when light is just falling on the metal surface, so there is a continuous supply of energy. So, according to wave theory, light of greater intensity should impart greater kinetic energy to the liberated electrons. Hence, the intensity of light is the energy delivered per unit area per unit time. It is the energy delivered in unit area in 1 second. So, but this has not happened in the experimental results. The experiments show that maximum kinetic energy of the photoelectrons emitted does not depend on the intensity of the incident light. But actually on the basis of the wave theory, it depends maximum kinetic energy and the photoelectrons are emitted just having a relationship. More intensity be there mean more maximum kinetic energy. But it is not observed in the practical cases. So, this is a first failure observed in the photoelectric effect by explaining it on the basis of the wave theory of light. Then the next point is, according to the wave theory, if a sufficiently intense beam of light is incident on the surface, electrons should be liberated from the surface of the target, however low the frequency of the radiation is. That is, even on the basis of the wave theory, even for a minimum value of the incident frequency, there should be a release of the photoelectron. But it is not happen in the practical cases. From the experiments, it is found that photoelectric emission is not possible below a certain frequency of the incident radiation. That frequency is named as threshold frequency. When the threshold frequency is reached, then only the photoelectrons be emitted. So, the minimum frequency, but on the basis of the wave theory, without any minimum value, whenever there is a frequency, even it be feeble, it be minimum, it is of low value, that should be emission of photoelectron. But it does not happen in the case of the experimental results, because the threshold frequency, below the threshold frequency, there is no more photoelectrons be emitted. After reaching the threshold frequency, the emission of electron be possible. But this proves just against the concept of the wave theory of light. Then the next point is the energy of light is spread across the entire wavefront. The electrons which receive energy from it are large in number. So each electron needs considerable amount of time, even it may be in hours, to get energy sufficient to overcome the work function to get liberated from the surface. That is, on the basis of the wave theory, there should be a time lag. That means when the incident light is just, when a light is just falling on the surface of the metal, then it should take some hours to release the photoelectron. But it does not happen in the case of experimental results, because the experimental results prove that when the incident light is just falling on the surface of the photoelectric material, then automatically, without any time lag, the photoelectrons are emitted. So the experiments show that the photoelectric emission is almost instantaneous process. The time lag is 10 power minus 9 seconds. It's very small value. Within 10 power minus 9 seconds, after falling the surface of the metal, it emits the photoelectron. So the photoelectric emission could not be explained on the basis of the wave theory of light. First, we are going to see about the one example. In the example, we are taking the cesium metal. So for example, this is just taken to be a cesium metal piece. For the cesium metal piece, the kinetic energy maximum, that is nothing but K max. That is nothing but the maximum kinetic energy can be represented as K max. This K max depends on the incident intensity of the incident light. That is, let the intensity of the incident light be. We are going to see some examples. First example, we have just taken the cesium metal. For example, this is a cesium metal. For the cesium metal, the maximum kinetic energy be just represented as K max. The maximum kinetic energy value be K max. This K max depends on the intensity of the incident light. Let the intensity of the incident light be I. So this K max value just depends on the value of the incident light. Then the K max does not depend on the frequency of the incident light. Let the frequency be nu. The maximum kinetic energy is not just depending upon the value of the intensity of the incident light. The third point is the time interval between the incident of light and the ejection of photoelectron is very long. That is, when in the cesium metal, when the light is just falling on the surface, it takes more time to release the photoelectron. So for the by simplicity, the following standard assumptions to be made. First assumption is light is absorbed in the top atomic layer of the metal. That is, when the light is just falling on the surface, we assume that first assumption is the top layer absorbs the light rays. The second assumption is for a given element, each atom absorbs an equal amount of energy, and this energy is proportional to the cross-sectional area A. So we have taken an element means one portion. So each atom absorbs the equal amount of energy. So this energy is just proportional to the area of cross-section. So we are just considering a circular cross-sectional view. So the area B, cross-sectional view of the B A. Each atom gives the energy to one of the electron. So after getting the energy, each atom gives the energy to the one of the electron. So the work function of cesium, we have known that 2.14 electron volt. That is the work function phi naught. The work function phi naught for cesium metal is, the work function is 2.14 electron volt, and the power absorbed per unit area is 1.6 into 10 power minus 6 watt per meter square. That is 1.6 into 10 power minus 6 watt per meter square. 10 power minus 6 watt per meter square. So here the work function phi naught is equal to 2.14 electron volt, and the power absorbed is equal to 1.60 into 10 power minus 6 watt per meter square, which produces the measurable photocurrent of the cesium. Here, first we are going to explain on the basis of the wave theory, we are going to explain the concept. The energy in a light wave is spread out uniformly and continuously over the wavefront. For example, this is a pond surface. For this pond, I dropped one stone here. Then what happened? The waves are just moving towards the edges, and first initially they are very closer with each other, and when they are just moving outwards, the extension of the waves will just be made out. So in the case of the energy up here, it's a spreading of energy. The energy of light is just spread over the thing uniformly. Then on the basis of the wave theory, the energy in a light wave is spread out uniformly and continuously over the wavefront. That means, for example, this is a pond surface. I dropped one stone here. Then what will happen? Here the waves are just formed and they are just moving. It spreads out uniformly. So the path is just known as wavefront. The energy absorbed by each electron in time t is given by E is equal to IAT. The energy absorbed E is equal to I into A into T. That means here I is the intensity, A is the cross section area, T is the time taken to reach that level, E is the energy absorbed by each electron. When this energy is just absorbed, the most energetic electron is released with maximum K max by overcoming the surface energy barrier or the work function psi naught, and this is expressed as K max is equal to I naught. This K max is equal to, the work function is phi naught, which is equal to IAT minus phi naught. When the electrons are crossing the surface barrier, then only the photoelectrons will just be emitted. So the wave theory predicts that for a particular unit time, low light intensity will just be falling on the surface when this value I is lesser than phi naught. The K max value is equal to IAT minus phi naught. Here K max is the maximum kinetic energy, I is the intensity, A is the cross sectional area. So we have just considered as a circular cross sectional area for your time interval of t, then phi naught is the work function. So on the basis of the wave theory, in unit time, low intensities are just be observed when IA is lesser than phi naught. No electrons be emitted. When IA is lesser than phi naught, that is up to threshold frequency, there is no more emission of electrons. So when the electrons are crossing the threshold frequency, then only the photoelectrons be emitted. So at higher intensities, when IA is greater than or equal to phi naught, when IA is greater than or equal to the work function phi naught, then electrons are emitted. So this implies that higher the light intensity, the K max value be higher. That is, maximum kinetic energy value also just be increased. More intensity of the light is just falling on the surface, K max value high. Lesser intensity of the light is just falling on the surface of the metal, then the K max value is low. So the K max is dependent only on the intensity under given conditions. That is, by increasing the intensity, one can produce the value of the light. So the K max value will just be given on the basis of the photoelectric effect. Even if the frequency of the threshold, after reaching the threshold frequency, emission of photoelectrons be possible. Below the threshold frequency, there is no more emission of electrons. Here, this cannot just be possible in the case of wave theory. So the wave theory cannot just explain the photoelectric effect. Then according to the wave theory, the intensity of the light wave is proportional to the square of the amplitude of the electric field. So that is equal to E naught. So on the basis of the wave theory, the intensity of the light wave is proportional to the square of the amplitude of the electric field. So what is the amplitude value? That is equal to E naught square. So the amplitude of this electric field increases the increasing the intensity and imparts an increasing acceleration and kinetic energy to the electron. So when we are just replacing the intensity with a quantity proportional to the E naught square in the equation 1, then K max should not depend on the frequency of the incident classical light wave, which again contradicts the experimental result. So here when we are just considering the intensity of light, which is just independent upon the facts. Then if the next point to discuss is, if an electron accumulates light energy just enough to overcome the work function and it is ejected out of the electron with zero kinetic energy. Therefore, from equation 1, the zero value is equal to 0 is equal to IAT minus phi naught. So, stopping potential, that is, there is no more electron emission be there. So, the electron particular light energy just to overcome the work function. So, the electrons emitted just having zero kinetic energy. So, 0 is equal to IAT minus phi naught. From this equation, IAT is equal to phi naught. IAT is equal to phi naught. So, the value of T is equal to phi naught divided by I into A. Here, the value of which is equal to phi naught divided by intensity of light I into, it is A is a circular cross section. So, for a circular cross section, the value is equal to pi r squared. The value is equal to pi r squared. So, by substituting the value, phi naught value, the value of T is equal to 2.14 into 1.6 into 10 power minus 19. 10 power minus 19 divided by, what is the value of 1.6 into 10 power minus 6? 1.60 into 10 power minus 6. Pi value 3.14 into, for the particular metal, the radius is equal to 1 into 10 power minus 10. So, 1 into 10 power minus 10 whole square, that is equal to whole square, which is approximately equal to 0.68 into 10 power 7 seconds. 10 power 7 seconds. This is approximately equal to 79 days, which is equal to 79 days. What it means? Here, when the incident light is falling on the surface of the metal, it has to take a long time to eject the photoelectron. But the experimental results proved that there is no time lag. When the incident light is just falling on the surface, incidentally, the photoelectrons be ejected. So, these are the contradictory effects on the experimental result and the wave theory.